So let's get started. So the goal today would be to I think we should be able to almost finish the slide for the random variable, and then hopefully Friday we will be able to continue the Excel, and then should be done with the first half of our course, which is descriptive statistics. And after that, we talk about how to handle data. And so far, we didn't. I already talked about data, right? So, but nevertheless, let's quickly review. I don't spend too much time to review that, but still, it's very important to talk about the definition of random variable. Do remind yourself that random variable is not the variable that is random, right? Rather, we are going to the idea that we are measuring the outcomes of the random experiment, right? It's like you have an event or an outcome from the random experiment. You try to give a number to each outcomes, and you try to put meaningful number there, right? Otherwise, if you put if arbitrary number there, it's not very meaningful. And the reason you do that is one is something you can measure, is the random variable. Second is it must simplify the sample space to the thing that we care, right? Just remember how we talk about the data type, right? There's a discrete or continuous, right? They are all numeric variable, right? You can imagine you can put ordinal data or category data, but in those cases, it doesn't mean too much when we talk about the mean and variance, if you recall the idea. So very quickly, we have continuous and discrete random variable, and discrete we have big P, right? Because this is give us the you give me the X, I give you the probability, the random variable equal to that X, right? And you have the big F, which is less than or equal to, right? And then you could know how to change from big P and big F to big P. You can do one way or the other because they're the equivalent way to say the same thing. And just to recall why we have this, because we know how to define F in continuous random variable. P is not well defined because P is always 0 for every point you are giving me. So that's why we have to do the big P and big F. And the big P and big F's very often is very complicated. So we have the what to calculate. We look at one number with expectation, give us a better way to describe what's going on there. And we also have the variance that give us how good is that data, right? And also we have some property of the mean and variance, like the linear property of the expectation, and also some property is like some square term, right? Is if you remember, this is the start and the cache idea, and various measure risk. Although I pitch here in discrete random variable and everything holds for continuous random variable there. So that's why you don't have to worry about integration. All the formula works very well. Even this, I don't have P, but I have F, but I have to use integration. But in our class, we don't require to know calculus, so this would be something that we will leave it for your future studies. And then we talk about by very random variable, and you have the joint probability distribution, and then you have the expectation of sum is equal to sum of expectation, and the sum of the variance will be equal to variance sum if they're independent. And if they're independent, then you have to add the covariance term. So that would be very important because that is the basis for you to do portfolio optimization, where you choose different investment to make sure that you are maximizing your expected return, but you also minimize the risk, which is measured by the variance. And we have covered these 5 important distribution, and that will be very helpful when we talk about continuous. And the uniform is everyone is equally likely, so 1 over n. And The polynomial with the basis for we to build up almost everything there. Okay. Polynomial is you have two types of outcome, success or failure. It doesn't mean that the random event only have two choices, but you only consider the outcome have two parts, success or failure. Right? Just imagine that the when you take an airplane, right? There's only two way, right? Either is there's no failure in the engine, everything works very well, right? But there's a delay, then you happen to be if one thing doesn't work, then you get a fail, right? So that would be the idea, right? Or in exam, right? You pass the class, right? There are many ways you can pass it, right? You can have 50 points to 51 to 100 points, everything you pass, right? Fail is from 49 to 0, right? So there are many ways, but you only care about number of success, right? And the P will be given by this rather not very beautiful formula there, but and we also have the mean and variance to describe the big P, right? And after that is binomial, which is the single most important thing, right? Because this is closely related to the normal, right? And you can imagine a binomial would be the one that have you're considering that you have a n different binomial trial, and you can imagine there are n boxes there. You open each box, and each box is identical, have probability success p, right? And then you have open n boxes. In all together, how many success you got, right? You have 0 up to n, and the big P will be given by this formula. And as I explain why we have that, but if you don't really want to know, or you don't really remember, or you just feel free not to remember this one, because you just knew this only formula, right? And since the P is so complicated, right? That's why it makes sense to talk about the mean as NP and the variance as NP times 1 minus P. Okay, so that is the main idea behind. And there are a lot of calculation goes on there. Probably at this stage, you don't really know whether you know it or not. But assignment we given, I think, this Friday, or then you will know little more about, or if not Friday, will be next week. You apply the thing into practice, so you know what to do. And as we said, the binomial is the basis for the rest, right? Poisson is just the case of binomial where n is very large, p is very small. It's very useful to model how many customers arrive over a period of time. So it's a given time period, how many things can happen, right? How many events happen. So that is very useful to model time dimension as number of things to happen, right? Because discrete random variable is Poisson. And later you will see the time for thing to happen will be exponential. We will talk about this very soon. I'm going to talk about that as well, right? Last class. And this exponential will be this formula, and particular mean and variance the same. Okay. And then after that, we have another very important distribution we'll be using a lot of time is called hypergeometric. The idea would be saying that you have a big n of items, out of which big A is good. You're going to take small n out of it, and you ask how many of them are actually good items. Okay, so this is a sample without replacement. It's very good for quality control. You do audit, you do various stuff, right? And if you go to some places, you don't go to the other one, then that would be the idea, right? So that is the P function is rather complicated, but the mean actually is not different from the binomial. It's still NP, right? And the variance is very close to NP times 1 minus P, but with a correction term at the very end, this guy, right? So this is NP, right? Because P is A over N, right? If you just draw once. And this is NP 1 minus P. So in terms of mean and variance, right? Sampling with replacement and sampling without replacement would not be too much different in terms of mean and variance. Of course, the probability can be very different. But you do notice that both of them seems to be very similar to the you can see this is the pink and the purple one do similar to a bell curve. Later you will see actually that's true. If you increase the big N to very large, they are really close to the bell curve. Okay, so that's why we learn the bell curve, the Poisson, binomial, and hypergeometric. When N is big enough, is bell curve normal, and that's why our second half of our course, which will be happening next week onward, we'll be basically doing bell curve for the rest of the semester, because in your application these days N will be large enough to apply the bell curve idea. Okay, but when you're not talking about data collection, you try to model things, you still require this, right? Remember, you go to do audit, right? This is the idea. You don't have a large sample, right? There's a limited warehouse you can visit, right? So these are the problem that you can't really rely on bell curve. Or you want to model how many customers arrive using a Poisson, then bell curve doesn't apply easily, right? You collect data, then you can probably apply bell curve because you can collect many sample as you want. So there's some idea why we still learn this way. You may ask, okay, if the bell curve is so good, then why we learn all that? But still, in many application, you can't really apply the bell curve idea directly. Okay, I hope that make a lot of sense to you. I would recommend you read this when you are stuck in the assignment, because they give you an idea how to apply. So I hope that would not be, it will be okay if I don't give all the details here. And next will be our continuous random variable. Well, we cover that, and this example explains why it's not possible to do P, but it's still meaningful to talk about F, because it's uniform between CO1. P is 1/2 and 1/2, and the F is a 45-degree line. And you keep increasing the P, then the height of the P will drop, right? It's 1/3, right? But if you can see this height is 1/n, and then oh, sorry, it should be blue, but I don't know why the screen gives you the black, but anyway. And in any case, if you increase this height to infinity, well, very, very large, this become very small, then this ceases to be useful, and this is still a useful one. Okay. And the most important part for continuous random variable is the big F, right? Big F is the probability that X is less than or equal to a number, right? And the probability between two numbers will be the difference between the F, and probably larger than will be 1 minus F. This is coming from complement rule. This is coming from addition rule, right? Or total probability rule, as you want. And one thing, if you learn M1 and M2 math in Hong Kong, they probably learn calculus, then you probably know that F, if it's smooth enough, which means it's differentiable, it's very smooth function, then you can always find a other function called small f, which, if you look at the area, give you the original big F. What I mean is like this, right? If you learn calculus, this is just integration if you learn calculus. And if a big F here, right, big F will give us a probability less than or equal to that number. But you can conveniently write everything in a small f, in the sense that the area up until A will be the value FA. So this area, the size of the area, will be equal to F of A. So that's how big F and small f are connected. So basically, the area under the curve on the left-hand side of the A will be the big F of A. Okay. This is, if you learn, this is what we call the fundamental theorem calculus, right? But not asking you to do calculus. So just say there exists some function that always exists for our purpose in our class. The big F and small f are related by area under the curve. And the red area will be 1 minus FA, and the area A and B will FB minus FA. So you may ask, is there magic? Yes, there's always a magic which works. If you learn that is like 500 years ago, invented by Isaac Newton, and his contemporary, the Leibniz, then there's a calculus problem. But anyway, You want to calculate this will be the idea in the black. I'm not going to go about that. But it does mean that look at the density function. Don't tell you the big F function is or small f function can be very complicated and very ugly to work with, and that's why we often would care about two numbers that summarize the small f or big F will be the expectation and variance, and the calculation behind requires some calculus. Okay, and in this class, since we don't, but the intention is the same, right? Suppose we repeat this experiment many times, and we got all the outcomes, and we convert each outcome to number by random variable, and then you look at those numbers and average of those number with expectation and variance of those number variance. So, but the calculation actually we have to do is to do the calculus. So I'm sorry that since a business class, this is what it is. Okay, but in the case if you really go to stat department to further your stat again, then you have to know calculus. So just to let you know that it's something that will be there. You can't really skip this one. Otherwise, you don't fully understand what's going on. But for our purpose, it's okay. So now we know that to describe the continuous random variable, we have two things: the small f or big F, right? And they're too complicated, then you use expectation and variance, right, to summarize those. And of course, we want to really get into the business is to apply them, and then that would be 6 of them, okay? And first 3 we will use it directly, okay? We can use it applied to, well, it's Halloween style exit. Over there is it's too early. It's still few weeks before, but there's a uniform. We can say uniform distribution is the maybe a binomial. Well, anyway, so a uniform distribution, exponential, and normal. These 3 will be can be used directly. Okay, so it can be used as modeling things happen in the real world. And the chi-square student T and F I introduced here, they will be used in the second half of the course. So you can't really use it right now, but I tell you what they are. But I just introduce them without going into detail because I just have 1 or 2 slides for each. But I tell you what they're using, and this actually starting from normal, the last 4 will be the thing we use for the rest of the semester. Okay, that will be the key of this. Why? Because they will be very useful for analyzing data. You collect information from the data. You want to extend the data knowledge to what we think about the general world because the data is specific, right? You want to draw a general conclusion. It require you the information of the knowledge of normal chi-square student T and F. Okay, so this 4 will be used for the rest of the semester. So you will not see the exponential. Unfortunately, you say hi and then goodbye, and hi and bye friend, and same as the uniform. So you don't see them again. But the normal student T and F will be there. Chi-square by itself is very useful, but in our class we don't have time to go over them. But we just basically normal student T and F. Okay. So uniform, and I think it's very simple. Uniform is just saying that if uniform between A and B means that any value between A and B is the same. Okay, and that means that if you give me two of interval between A and B, as long as the length is the same, the probability is the same, right? So that's why the F function is a flat line, because as long as I give you any interval, say suppose, have same length, maybe length of 1 or any unit, I pick another interval, it's still a 1 unit interval, then the probability that the random variable between the first interval should be the same as second interval. That's my mean uniform, right? Doesn't really matter what number you pick, right? As long as you tell me the interval, the same length, the same, right? That's why uniform, right? Why I have to call interval? I can't say one number because the probability a certain number will be 0. So for probability statement to be meaningful in continuous, you have to say interval, right? More than one number, right? You have the infinite number, cannot be a finite. If finite number of them will be 0, right? So you just say the interval, right? And the probability of this interval, if you remember, the idea of this big F is the area below the curve, right? So basically it's just the probability that if you want, this will be the probability that the random variable is between these two numbers, right? And same as the idea if you ask, right? This is the same, right? So you can see why it has to be a rectangle, because the probability is based on the area, right? The same base, and only rectangle will give the same height, right? So you can't be triangle, it can't be any other shape. So by construction, it must be a rectangle, right? And because this is a rectangle, the big F must be a upward sloping line, okay? Because this is the area, right? Area of the rectangle. I mean, the longer the base, right, is proportional to the height is always the same, right? It's proportional to the base, right? Because the rectangle is base times height is the area, right? So that means that must be the same height, right? So you move, then it must be this one, right? So remember what is it, right? Suppose this is called C, right? Or then this area, this height, this is called f of C. C is why you can use the pen. And really the pen that doesn't work. The pen doesn't work. Why to put the pen here? Okay, anyway. Or I don't know how to use the pen. Okay, f of C here. Okay. That means that if this is the C, the color. Maybe I just erase it, right? Because seems to be a little bit too congested. So it will be C just mean this area is f of C, right? So this area. So this is how the big F and small f related, okay? I don't, if you learn calculus, you notice integration give you the big, small f give the big F. Differentiation of big F gives small f, right? But if you don't know calculus, that is same as you stacking the area, right? Just same as what we say, stacking area, give this guy, right? You unstack the area, give this guy, same, right? You imagine you cut this way, small, right? You stack the area, you can also stack the same thing. The height will be the stack up thing. So the intuition from discrete actually go to continuous, okay? But of course, if you know calculus is very straightforward. But if you don't, you can take the intuition you have from the discrete case, you stack the small f, you get the big F, okay? You cut it into small pieces and stack it up. The area is just the height, okay? And the reason why I talk about uniform, of course, uniform by itself is very useful benchmark. If you don't know how to model, I think uniform is the easiest because why? Because how you can apply in practice, A will be the thing from the data with minimum from the data. B with the maximum from the data, right? So suppose you want to model, okay, stock market, right? You don't have good idea, right? And then people said, right, the stock market today may be from 26,000 to 28,000, right? And then you don't have good idea what's going on. It's uniform will be the thing that fit easiest, right? Because you don't really know. And to have more uniform, it's very simple, right? Just tell me the mean, the max, and you're done, right? That's A and B, right? So that's the easiest way to model. And it's usually this is the first number I come up with your head, right? And that is easy, convenient find data, right? Because you don't have any minimum assumption. And probably you say, okay, you say uniform the real thing, but you learn the base theorem. You start with uniform. You can update your P. Of course, this is beyond the scope of a class. If you go to second or third class of statistics, you learn how you can update this through starting from the minimum maximum. That's for data, right? Minimum assumption, you can keep updating your learning things, and you can have a more realistic one, right? That's how you train things from the data, right? And then that is also how, right, AI being trained, right? Start from things uniform and then keep training until you reach the thing, right? So it's not something that a naive guess is the thing that we think that is fitting. And the big F will be that simple function. It's upward sloping line, 45 degree, right? This guy, right? 45 degree line there. Sorry, not 45. It depends on the slope is 1 over B minus A. And the this is still some of you think it's complicated. So probably you have to remember the mean and variance, how to calculate, right? Mean is just the midpoint of the highest and lowest, right? The middle. And the variance with the range, B minus A square over 12. And then 12 I can't explain, but square would be the thing we know how to handle that. And this is the type of the graph. You will see this A, this is the A is 2, B is 3, A is 1, B is 5. Do remember the area under the F must be 1. So that's why when you A and B are shorter, then it must be higher because the height is 1 over B minus A, right? If you remember. So here's an example that how you can use the uniform, right? And very often this is the thing we expect, right? The news that the rainfall follow a distribution between 1 mm to 4 mm, right? And if you don't say anything, the uniform is the thing that you assume, right? And the mean will be just the average. It's just A plus B over 2. And the variance is B minus A squared over 12. So that's how we calculate the distribution. And of course, you can also calculate probability, right? And either you can draw the graph, right? Or you can use the formula, right? Because between 1 and 3, right, is simply you have 1 here, you have 3 here, right? The F is like 1 to 4, right? 1 to 4 is here. And the height is what? The height is actually 1 over 3, right? And the base just 2, right? This area. 2 times 1 over 3, right? It's uniform between 1 to 4. It's a rectangle. And the height is 1/3. Why 1/3? Because the area, the whole area must be 1. And the width is just 3. So must be 1 over 3. And you only ask 1 to 3. The base is 2. The height is 1/3. So it's 2/3. Okay? Or you can apply the formula directly. It's looking at the area below 3 and area below 1, right? That is that's a formula there, right? So you can apply that as well. So I think that shouldn't be a big issue for you, right? Just this F of 3 and F of 1, just apply this formula directly. Okay. So I don't see you have a big question, and then you can do the same for 2 and 3. I mean, if you still have problem, but then let me know. As I said in the Friday. So if you have question, please do ask TA. Schedule appointment with her, because I think this is for many of you already. You don't read this already, so I can't really go too slow on this one. But you can ask me during the break, or if you have any problem, let me know. So now we go to exponential. Exponential is just the Poisson idea, right? If you remember, Poisson is over a period of time asking how many success, right? Just let me draw a picture, because, right, just like period of time, right, you would ask how many success you have, right? Maybe 1, maybe 2, maybe 3, right, over this period of time. And how many of things can happen is random, right? But if this is followed Poisson, right, and we will say the time for things to happen, this time period is continuous, right? This will be follow a exponential, okay? And it doesn't really matter which one you pick, right? You can be from this one, or you can between the second and the third, or between first and the second, right? This is all the same, okay? It doesn't really matter exponential, because remember, they are independent, right? This comes from binomial. Binomial is every occurrence is dependent. So the time is red, same as green and blue. So that's why we only have to model exponential is things to happen, right? If once thing happen, the next one will arrive will be will have the same expectation, okay, with the same distribution. So it doesn't really matter. We'll talk about what is waiting time until a success, right? So it doesn't really matter whether how many success has done before, right? We just wait. And the particular point about this is meaningless. It doesn't really matter how long you have been wait. Okay, if it doesn't happen, the time to happen will be the same. Okay, so I think I give you an example, right? It's very common in many village along the sea, right? There's always a stone. I don't know whether you know. Also, you can see in Hong Kong as well, right? If you see, right, there's a mountain here, right? And there's a seaside, okay? There's a sea, right? And if there's a village here, right? What happened is, or very often, there will be stone here, okay? And this stone will be thinking a woman or a man who is waiting for his partner to come back, right? And the partner never come back, right? Every day he just go there and wait and see whether his husband or wife is coming to come back, right? And they never come back, right? And people ask, he will be come back tomorrow, right? And what is it? Meaningless, right? Regardless of how many days he or she have been waiting, he's thinking that his husband or wife is coming back tomorrow, right? So this happened, right? So this is meaningless property, right? And and what is not memoryless? Okay, what's not memoryless? And I think there's a very famous story. Probably you know. I don't know whether you read uh, a novel. Uh, there's a guy, okay, and his wife, okay, his wife got poisoned, okay, and he jumped to the cliff, okay, and his wife don't want his husband to follow her, so uh, she write in the stone that she will come back after 16 years, okay, and the guy think 16 years he just keep waiting, and at the end, he wait 16 years, then he eventually jump, okay. If you don't know what is, that is 楊過小龍女. That is what happened, right? 金庸小說. I don't know whether you know it, but that's what happened. That is not memories, right? Because she think that after 16 years, she will be forget, right? Of course, at the end, I mean, the lady actually survived in the under the cliff, but that is not memories because after 16 years, actually he think that is over, right? But for the idea, right? This Mont Fuset is actually still there. I mean, if you don't know, I mean, in the Lions Rock Mountain, right? City San, and there's some rock over there as well. But okay, so that's what memories. And this very interesting method of property is not just apply for this kind of rock. Actually, it's more common in engineering. If anyone study physics, that is the nuclear reaction. It's the atom, whether they emit the electrons, or the nuclear reaction is follow exponential, right? In the atoms level, right, there's some nuclear reaction goes on, and once it happen, it's stochastic, right? But when it happen, is follow exponential, and the exponential is mean that the f function look like this style, okay, and later you will see it's just like this, right? Just like it's a dropping very fast. That's called exponential, right? It's not dropping very linearly. It's dropping very fast. The f is like a cliff. Okay, it's very likely at the beginning, but slowly, less likely. Okay, before you stop. Okay, the big F is like this function. Okay, and um, the E is just a constant number, 2.713. That are Euler's number. That's why the E. And turn out that the mean is lambda and the variance lambda square. So although it's come from Poisson, the mean and the variance are not the same. So just make sure that you know what's going on there. And give you an example before that is exponential, so it's like decreasing. Okay. And I think with the example, say the time for customer to arrive follow the Poisson. Okay. Follow exponential with mean 20. Okay. So that means that our lambda is 20. Okay. Because our lambda follow from Poisson, right? It's 1/20. Okay. Because our lambda is the arrival, right? So mean 20 minutes is 30 minutes will come, and our mean is 1 over lambda. So that's why we have this equation. And if you remember, 20 minutes means something like this. Exponential, right? Exponential like this. And 20 somewhere here. So the question is being asked is, okay, next 10 minutes means I'm asking 10 here. I want this area. Okay. Okay. And f of 10 is given by this formula, right? Is f 1 minus 1 over lambda x, right? And that would be the idea. Okay. So that would be the probably that the time that happened is within the first 10 minutes. So this is rather useful. And the question we will ask, how can we get the 20 minutes, right? That's from data, right? Although we don't talk about the data, but how you get 20 minutes is come from data, right? So that is, I didn't talk about this in this class, but this is the method is called method of moments, which is using the data, you have the mean and the variance, and how you estimate or how you get the lambda or n or p in binomial and those or na in the hypergeometric actually come from the data. From you can look at the data and see what are the means, and you can solve system of equation and get your parameter there. In this case, you just feed the data, look at the data, what is the sample mean of data, and this is the case, right? So for example, for this shop, right? Look at the historically, how long does it wait for one customer to arrive, and look at the historically made data, and that would fit the model. Okay, that's how you get the 20 minutes. But how to actually apply this, there you will be learning it in other classes. So our class is basically just tell you the methodology, okay, and how to estimate those is coming from data, right? Because it doesn't come from our head, right? Why 20, not 21, not 30? That is from the data, okay. But of course, in the way we do it, just the simplest one is called the method moment. Just look at what happened, right? Apply and get the lambda, okay. And same if you want 5 to 15, just take a subtraction, right? Because the idea is this, right? Again, the same, right? You have it's a color, right? Exponential, right? And you want number is between 5 to 15, right? You want this area, right? How do you find the red area? The thing is, the big F will give me the area under the curve, right? So remember this curve is F, right? So the big F function tell us what's going on the left-hand side, right? This is the F5, okay, the area given by F5. And I have this blue will give us F15, right? So the red is just blue minus pink with the red, okay? We'll be using this very soon when talk about bell curve, but that's the idea, right? The difference between the two big F gives you the area in between, right? Is that okay? Is that okay up to this point? Okay. Now, before the break, I want to talk about the normal because I think that would be very nice. I just delayed the break for 5 minutes, so not too long. So hopefully it's still bearable. You still have some attention. I know you must be very tired when you sit down. I mean, especially after the holiday, we are not back fully yet. So I just keep it simple. So normal, also known as bell curve, or standard bell curve, and is a thing that you can find very often in real world a lot. Sometimes this is invented by mathematical Gauss. So sometimes you can see old textbook they call Gaussian distribution because this is who invented that. And but it's so common, then that's why have the name normal is something that if this is not following this is abnormal. So that's what it means. Normal is like so common is seen, and it's the bell, but the math function, if you don't like math, is rather ugly, right? You have a pi, your square root, exponential, right? Of course, if you're a true mathematician, you find very, very beautiful. But if you're not a mathematician, you think it's very ugly. Okay. But uh but I will try to explain why you have pi. Okay. But anyway, lucky good thing is this F is so complicated. Even your friend who major in math cannot do it by hand. So that means that we don't have to worry, right? I have a calculator table. So our class will focus on looking at table. Of course, we teach you how to do Excel, but that would be the calculation. So we don't really worry too much about that, but we'll be using it all the time. So we are looking at table many, many times. That would be useful for exam or assignment. So we're looking at the table. And because this F can be calculated directly, so we will be looking at the big F thing. Okay. And uh, try to convince you why this is the bell curve is useful, because it's so common, and I will try to give you the idea is later you will see why it's so common, because everything naturally occurring actually follow normal. Okay, and you will see IQ, weight, height. You try to collect data, is almost always is normal. And let me explain one of the reason why you see all these naturally occurring observations are normal, not just human. Look at animal, all the same. Okay, one of the reason is we are what we saw today, or friend or yourself, is kind of outcome of random process. Why? How you come? Okay, suppose you're a normal human being, right? You must be half of you come from your dad and half you come from your mom. Okay, this the chromosome, the material, right? And what do you mean by half come from your dad and half come from your mom, right? Half of your dad is not your dad choose which half to give you, right? It depends on the cell division, and the half is pretty random because you know the chromosome material, right? Basically, how you get the 24, 23, I don't know how many, 20 something chromosome, right? Depends random. And which sperm comes to which egg is also random, right? So that means that since you're born, the part come from is also random. And how you grown up, who you meet, which day you're born, what the temperature, the weather throughout the year, what kind of food you eat is almost everything's random. Okay, so that's why for the society, if you collect IQ, weight, and height, everything also will come from many different random process, right? Because what you eat today, right? You don't really know, right? How can you know, say, what you don't eat, right? You go to the canteen and when to pick up something, right? So every day, maybe it's very hot, and you want to eat some spicy food, right? It's very cold, you want to have a hot drink, so on and so forth, right? So these are all the things turn out to be, later you will see, if things are random, add together, will be a bell curve. Okay, I will talk about this, and then you should understand this is the, I think, most important theorem from our class beside base rule is called central limit theorem. Turn out to be everything, loosely speaking, is if things come from randomness, you will see a bell curve. Okay, it's a lot of if loss of randomness end up to what you're measuring, you will see a bell curve. Okay, so that is the idea behind the bell curve. And the bell curve, I talked many times, will look like this. Okay, will be a bell curve like this, and then just one more minute. It will be governed by one thing, two things, is the mu and sigma square, and you'll be not surprised, sigma square the variance, mu is just the mean. Okay, and that means that for normal distribution, you only need to tell me the mean and the variance, then you're done. Okay, and the mean govern the location. You can see the blue and the green just have the different mean, but same variance. Okay, and compare the green and the red, same mean but different variance. And do remember that the area under this F must be 1. So if you have higher variance in the red one, that it will be much flatter and much shorter, right? Because area must be 1. So if more spread out, it must be not as tall as possible, right? The total volume or the area must be 1. Okay, so this is the thing, and then you can see immediately see the convenience of normal is as long as you tell me it's follow normal, okay, which often happen to be a many natural occurring phenomenon, and I only need to collect the data of the mean and variance. Once I've done it, then I can easily model the thing because that is tell us the mu and sigma square. Okay, so that is highly convenient, right? I have a data, I estimate the sample mean, sample variance, and this gives us a simple model to predict the future, right? If I think, right, for example, if you want to think what is the height or IQ or the weight of your next customer, right? How can you do that? Right? Suppose your education or you are selling clothes, right? You want to know the height and the weight, right? Then you think that is follow normal. Then you just look at the data, what's the mean and variance, and you can think about how to plan what kind of inventory you can put in your fashion store, right? You'll be look at suppose, right? You are going to a store, you have prepared different size of clothing. How can you do the preparation, right? And you at the societies, you should follow normal, right? And as long as you know the mean and the variance, you're done. You know the shape, and you can do all the calculation. We do talk about this more after the break, but you will see this is very versatile, and I would say, I mean, if you forget everything, right, from this class, the bell curve you will never forget for the rest of your life because we'll be doing this for the rest of the semester. So that's a break of 15 minutes. It's a promise. I delay 5 minutes or six from yeah, 5 to 6 I think 9 minutes. I will give you 9 minutes more. So let's resume at 11 11:40. So in the meantime, I would be grateful if you help me to fill in the you reply as a way to know your participation. Okay. And if any question, feel free to let me know. I just get a coffee first. I'll come back for coffee. You can tell me. 你覺得我呢方面都有啲真係冇嘢。我覺得你有啲真係。而家都冇 midterm 喎，唔使咁緊張，我冇 midterm 嘅。我喺中大教過都未試過有一次俾個 midterm。咁咪好咯。因為我覺得 midterm 大家都已經咁繼續讀咁多科，點好多 midterm，所以我就俾 midterm 大家。真係。但係如果大家其他科冇 midterm，可以俾下 midterm。midterm 就我唔使嗰度分嘅。全部要長。你喺度多長？係呢個唔係呢個係其他人點行過都睇下。係要 production 對住呢度。對住你。因為有人我 area 嘅 office。係啊，我話呢個成啊，因為我真係不明白清楚啦。我佢時間睇佢計數時間，我一個人 screen 晒我又，真係差啲係 screen 晒。
都其實未必啊，不過我係影下，因為之前真係出名，哦，要 P 翻。我都有影下，現在就係發生報告嚟。我上次佢但係佢話4點半去到1點，但我唔係覺得個 stop 正，所以我佢邊係10樣嗰隻。入嚟真係我在玩下我會。但係呢個就冇咯。幾時啊？紫色就係理論，綠色就係實踐嘅實際，黑色就係即係第一件事話，如果真係想知嘅係想知嘅係建議你係紫色嗰啲就做呢出嚟，希望你明白咗咩事。咁綠色嘅影響，即係至少你對呢啲影響係綠色嘅識得咗。應該係讀咗出嚟，考試100%喺個8、9成都佢答唔出。我話呢個哦，我成日好想。Yeah, so okay, what? Answer. 你教下佢200幾人先，做得幾好。幾好嗰時，exhaust。
哦，唔係，都係上面跌咗落地下嘅。
都係 general。CD 嘅時候，
佢有 apply，佢有 apply，直接。我 screen 到 whole 半個場。大概係讀咩？
睇下咯。
B.B.A finance。
都睇個位嘅。
答咗。
有啊。
我 UST。
哦，大概3個。哦，大概4個。
一路睇翻前面嗰個驚我唔記得。YouTube 做俾我係
係實現呢個教授。B.B.A 做咯。好。Hello。碟拋啦，幾層。我咧佢有，屌，因為佢嗰啲咩嘢高利貸嗰啲，嚟去哇，一翻幾成錢？百啲都哦，呢個都想死，百幾平方，即係兩嘢啦，後啲喎，我哋好啲咯，我哋講，都係得少，因為就玩，有得玩啊嘛，有得玩。ACC 係我哋咪 depreciation 啊，嗰個 lease buy 啊，係咪都係做 T account 嗰啲啊？一年就成收呢科，咁咪仲有一屆嘅新一屆，我係改頭嘅擴教室，明年中大7學咩人文科改革，咩全人舊嘅同地鐵度交地鐵，點解下一堂先？ 整個中大搞啲咩呢啲犯罪，佢哋係幸運者頭嗰一劫，頭一棍嘅，只一棍劫嚟刮成，劫嚟刮。
So maybe we slowly resume as we look at the data. Hi, no. Have a good day. Still being a cool lesson. Is it that cold? 24. Hopefully we still remain cold. What see you recommend the most? I actually, to be honest, this day I don't eat, so I don't really know. I mean, if you know me, I mean, actually, I skip my lunch at school. My canteen, I have some snacks at my office. So if you want some snack, you can visit my office. There's some snack there, but I don't. At the old days, actually, I go to CC canteen. For the lunch. Because I told you right, I don't have money, so I go to the I think I eat $10 meal. And used to be medical canteen old days have a very good lemon tart, but it's gone. And the canteen in the B school have a beef burger is very good. I mean, 50 something dollar, but they don't have beef burger all the time. Sometimes they have meat, sometimes they have pork, but the beef burger is pretty good, I would say. I mean, comparable to outside, it's a pretty nice one. And for staff, actually, I mean, I don't know if you have some staff accompany you. I mean, the NA canteen, the New Asia College, they have a very nice noodle. The staff canteen, that's a good one. It's not expensive. That's a good one. And what else? I think the rest, actually the staff canteen usually is pretty good, but you have some people to go with you. But also you can book as well. The what else? Yeah. Unfortunately, I don't eat that much, so I don't know too much about food. Unfortunately, I went to the class an hour early. Oh, sorry for that. Hopefully you can stay until now. Not many calculation. Okay. Maybe if you want, I can release the last year final exam now, because usually I will release in November because I don't want you to be nervous. But if you really want to be that early nervous, I can release. Then you can see. But okay, to put it now, the final exam would not be too much different from assignment, except you have less calculation. So I would say the final exam is easier than assignment in that sense. Okay. Because I don't do a lot of calculation there. So, but you will see, to be honest, even every year I have very similar question over the years, I still have a nice distribution. So so far I don't so far the 5 years, so every year is almost very similar. I mean, of course there's some minor changes, but I still have a nice distribution. So so I think it's more or less very consistent question I'll be given this year. So and you will see, I can give you the, if you want to be nervous, you want it, raise your hand if you want me to release earlier. Or you can, of course I'll release, but I'll release November. You want it earlier? Okay, I can. Okay, to be this way, I'll release earlier, but to avoid your nervousness in the midterm, you don't have to look at it, right? We don't discuss it. Don't ask us a question. We'll talk about this for the last week of the semester. So we'll talk about it in the class, don't worry. But don't ask question for TA for that. Don't ask me question or that. We are not going. We'll discuss the answer at the end, with the final last week or so. But that hopefully that will ease your concern. But and you don't. I will not give you all the past paper because they're always similar. So I just give you 1 year be sufficient because I give other year will be very similar anyway. Okay. I'll give it because since when it's midterm again, 24 already said no midterm, so no midterm. So for my class, no midterm. Okay. I already give you a quiz, right? If you really want, for those of you who really want to get a head of yourself, you have the quiz over here. The quiz 3 will be released after this week because quiz 3 is about the random variable. I'll put it there. But to remind you, the quiz is by attempt. So at the end of semester, make sure you go in and click submit, even though you don't do anything. Okay. If you do nothing, then I can't give you grade. Okay. So as long as you attempt, you'll get the grade. Okay. And I don't care how you do it. Okay. Just you do it, and then the answer is there, explanation is there. You have question, ask TA. So again, quiz is more difficult than your exam. Okay. Because I just want you to know what's going on. Okay. And the main thing, of course, in our course is basically the projects, right? I think the project actually can easily show whether you know or not. And actually, a lot of distribution come on the projects. Okay. Because I mean, you don't do a lot of time, you don't spend a lot of time on the project anyway, but it's easy to show you whether you know it or not. Some people clearly send me nonsense. And you would know. I mean, if a teacher, you would know. The formula, as I said, right, I'm not intended to ask you computation, right? So we don't really worry too much about the computation. It's asked in your assignment, you do in your projects, right? So exam, I don't think you worry too much about exam. Yeah. So difficult. I'm sorry about that. Hopefully, as again, please look for your TA if your question, and then you do the assignment by yourself. Don't put it on the AI and just submit that answer. It's going to harm you anyway, right? Because the distribution of the assignment is not a lot, right? Usually, right? I mean, just A minus or B plus, right? Usually there's 3 ranges, right? But anyway. Oh, what is today? Turn out to be someone think it's Thursday or Friday. Maybe that is very sleepy. Weather? Yeah, weather's good. That is a joke, but that's a key point. Small f is not equal to big F, right? If you stack the small f, become a big F, right? If you integrate the small f, become big F, right? If you like the calculus knowledge, but not the same. It's not equal to. Uniform and exponential is pretty useful, right? Because uniform is you assume it exponential time to arrive, right? But Poisson itself is very useful already, right? Poisson is modeling how people arrive, right? On hypergeometric and binomial also modeling how things are successful, how many items you got. So it's very useful. Linear transformation, I didn't talk about that yet. And normal, we talk about that as well. The bell curve, yeah, that's very important. Okay. Bell and 小龙女, yeah, that's what happened. So we have a nice bell curve here, goes on. What else? So I think there's some people who feel difficult, but I think we are mostly reviewing. As I said, this exam is open book. If you think it's difficult, you can just copy whatever you bring to the exam. But as I said, our class is not intended to ask complicated calculation. It's applying our knowledge in the practice. Okay, I think the exam is not difficult, but just you have to be fast because we are only give you 1 hour. So the question is not coming difficult, but whether you know it quick enough. That I think that's the main part. It's not something expect very difficult. I mean, everyone know how to do it. If I give you 1.5 hour, 2 hour, you can do it easily. But just ask you to do it fast enough. Okay, fast enough is not you write very fast, but you just look at the slide, you know where to look at it, and just apply it, right? If you spend the time study the notes in the exam theater, probably you don't work. But if you know where to find and you just copy it and do it, then shouldn't be a big issue there. Okay. Yeah, that's a good thing about a man, right? Men can always wear the same thing without an issue. And for my wife, even though he has a lot of stuff, I think is not enough. But unfortunately, that makes easier. Oh, that's a good one. If you cut a sandwich in half, is this 2 sandwich or half a sandwich? Okay, that's a good question. Actually, that's actually what doing by continuous random variable, right? There's always you always cut is still a sandwich. So no matter how many times you cut, it's remain a sandwich. Just like the random variable idea, right? No matter how many times you find a number, there's always number in between, right? So that's a math joke. But I think this is a 2 half sandwiches, if you ask me the answer. Right? 1 sandwich, you cut it into half, that means 2 half of sandwiches. That's my answer. If you want the answer from me. Okay, so far it's okay. So as we said, we go with the bell will be the big thing. Some of you asked me with the square root 2 pi. Do you remember? As I said, this f is just for you to know that something exists. And to be honest, I can't remember off my head, so you don't have to do it as well. Just if you see something like this, then it's a normal. But I don't think anyone actually use it. I never use it except the proof in the slide there, but I never actually use it at all. So of course, the main thing is this gives you the mean is mu and variance sigma square. Okay, the mu control where the bell is. The sigma tells you how flat the bell. Okay, so of course, if you still remember the first topic, beside mean and variance of 2 things, which is skewness and kurtosis, and the bell has skewness 0. Why? Because the bell is symmetric, and the kurtosis is 3. So actually, in this slide over somewhere here, right? The symmetric is kurtosis is 3. So excess kurtosis is always 0. So that's why we always compare to kurtosis 3. The reason is because normal is so normal. It should appear everywhere, right? If you're fatter than normal, then it's fat. You're thinner than normal is thin, right? So that's why we do the kurtosis compared to 3, right? And why we compare symmetric is 0 because normal is symmetric. So that is the reason why we do it. And one thing I have to remind you a little bit is the normal actually go from go from negative infinity to positive infinity, right? There's something that doesn't exist in all the other thing you learn, right? For the discrete, it's always from positive number, right? Positive integer, 0, including 0, right? And Poisson actually go from 0 to infinity, right? Poisson. And uniform, of course, give me 2 number, must be there, right? You can't be lower than, you have to know the lowest and the biggest. Exponential is always from 0, right, to infinity, right? But normal can be any number you think you apply. So that's why it's so convenient, every number, right? The difference between 2 normal is just where it locate and how spread out they are, okay? So that is the one key point I want to emphasize, okay? And you only need to describe a normal, you just give your mean and variance, I'm done, okay? And another thing is mean and variance are kind of independent, right? So you can change mean without changing the variance, right? It doesn't happen when you have a binomial, right? N and P are related, right? and the mean and variance are kind of related as well. So you can change one number, the other number will change as well. So now I have a technical slide to tell you why normal is so normal. The first one is, as we hint already, if you use Poisson or binomial hypergeometric, when the sum n is very big, it will become normal. This property we'll use 2 or 3 weeks later. Okay, so we'll use bell curve to do everything. Okay, when n is big enough. So that the first bullet point over there, and second bullet point there is actually with the physics as well, but that is a very simple thing. You can imagine there is a property of molecule, right, or atom, right? The center of atom is center. You can imagine it's a 2-dimensional space. There's a center atom is here, okay, and you can imagine there's an electron, right? There's something. The small thing is flying around, right? And if you know physics, right, electron is, you can't really find where is randomly located. It's follow some probability, right? And there's 2 property that for the electrons. The first one is it doesn't really is called radial symmetry. It means that where it is depends on how far from the center, right? It just depends on center. If we're far away, right, then it doesn't really matter. It depends on the distance, right? So that what I meant is, if I have this is the center of the atom, right? The electron, whether it's here and whether it's here, with the same, if the distance the same. If this is d, is it a d, the same. So that means that if I tell you the circumference, a circle there, same probability, right? The smaller the circle, maybe closer, right? But it just only depends on the distance. If you rotate the same thing, it doesn't really matter where you are, right? Because it's 3-dimensional, right? You look at this point, as long as distance from the center the same, it's the same. The second thing we want to have is called the independence of 2 dimensions. Means that if I tell you the electron is here, okay, it's x distance. This is 2-dimensional space, x and y, right? I tell you that if the electron must be in this line, okay, the same x, right? So maybe 3 from that, right? 3 maybe 3 millimeter, 3 centimeter from that, right? Suppose, right? 3 unit distance from that. Okay, I tell you this. I can't tell you what's y. X and y independent. Okay, tell you where the x is, doesn't tell you anything about y. Okay, if the 2 x and y 2-dimensional are independent, and the probability depend on this distance only, the only thing you can get is normal. Very surprising result. So if you have to follow these 2 conditions, probability depend on distance only, and telling you the x coordinate doesn't tell you the y coordinate. If these properties satisfy, what you only have is normal. So that is very natural thing to have in physics, and of course, it's also natural when you think about things happen in the world. That's normal. That's why in physics, you see the normal, right? What we call the Brownian motion, if you know, or random walk, is based on this idea. It's 2-dimensional random walk over there. Because anyway, and the last one is the most important, right? The central limit theorem is, as I said, beginning, the variable is actually follow many random thing, then it follow a normal. Okay, and that's why IQ height everything is more normal. So anyway, if you don't believe, it doesn't matter, because everyone knows it's normal, so it's going to be something up here all the time. Okay, and here I mentioned about some application in business that is important. So those of you who know investment, then the one thing is called asset pricing, and then that is something called the option pricing. And option pricing, the famous Nobel Prize equation called Black-Scholes equation, and basically assuming the stock price follow normal distribution. That is we have over there. And also, if those of you who learn risk management, and there's called risk value at risk, VAR, also shortfall also based on normal. Okay, of course you can do much more complicated, but the base thing you learn is having the risk depend on normal. And also, if you're talking about production, right, You do production, and then the machine and how accurate they are. Actually, most of them are coming from normal. Production, right? Operation is many natural process going to happen, right? Because machine depend on many parts, right? Suppose you are going to think about, say, the machine is going to fill up this can of coffee, right? And the machine process depend on many small parts, and turns out that the volume, right, is, although it said 250, right, but it's not exactly 250, right? Can be a normal distribution with mean 250 and the variance maybe 1 or 2, right? That would be something like that. So that everything follow normal. If you think about machines or even computer, right? Probably you would think now you're lucky, right? In the old days, now the computer never die. In my old days, I always see the blue screen all the time, right? I don't know whether you know blue screen, right? When you work out, then suddenly the computer doop, and then it doesn't work. I mean, I don't know, but you guys are too young to know there's a bug in the machine. But when I was that time, then machine always suddenly die and then restart the whole thing again. And also even the Microsoft Office sometimes just die and just kill itself. Okay, and that in old days is the thing, but now it's no longer dying, so much better. And you can do the normal distribution to model those kind of event. So since normal is so common, then we will have a notation to decide is normal. So that shorthand will say random variable x follows the distribution of normal with mean mu, variance sigma square. So this is the notation, not by me, but you can look at all the textbook. This is the standard notation. So let me read it. X, the snake thing is called follows the distribution of normal, and the bracket will contain some parameter, which in this case normal have 2, mu and sigma square. Okay, so there's nothing very deep here, but just the notation. I want to do this because that will simplify my life, get to make things easier. So it's okay. So now first thing is I want to surprise you with the bell. The first surprising observation is the following. I have a bell which is x is okay. I have an x, okay, with mean mu. The bell is centered here, right? And sigma square is the variance, right? So this is how I describe that. Okay. So now consider I draw a number there, okay? And whenever I draw this number, I multiply by A and plus B, okay? What kind of thing I got, okay? I close my eye, right? I draw things, I draw from the bell. What kind of thing I got? Turn out, very surprisingly, it is still a bell. Okay, I close my eye, I draw a bell. So basically I put a number there, I multiply by A and plus B. Okay. Or imagine the following, right? X is the stop price, right? I have the stop price, I have 10 of them, right? And A is 10, right? And B may be cash, right? I have a free share of a stock, a bond there, a cash there, right? My portfolio value will also be bell. If the stop price is a bell, my portfolio also a bell. Okay. You may ask, is it normal? No. Okay. In general, this is not true. Say, for example, binomial, you add some number, is not binomial, right? Because binomial come from 0 to n. You add 1, is no longer from 0. Exponential, you add something, is no longer exponential already. Okay. Anything you add, may uniform still yes, but in general, even uniform, you multiply, is not uniform. Okay. So this is in general not true. Okay. But what you know already is what is true is, if you remember the formula, E AX plus B, okay, it is still A mu plus B, okay? This is true regardless it's normal or not, right? This is linear probability expectation, right? It doesn't really rely on the bell, okay? Okay, and the variance of, sorry, I can't really write that clear because the pen is broken. It's always A square sigma square, right? So this part is okay, okay? But this normal is not normal, right? Because this is something, a result, right? We can prove it, but we are not going to do it. But normal, you add or multiply, right? It is still a normal. Okay. Okay. So this is probably only true for normal or some other thing, but most or only it doesn't apply to many other things. Okay? You multiply something, you add something, you no longer normal. Okay. But turn out that for the bell, it's very robust. Later you will see, no matter how you torture the normal, it's still normal. Okay, we'll show you later. But this is the first torture is to multiply it, okay, and add something. Okay, so it's still a normal. Okay, just to visualize it, X is the stock price. Okay, you have 10 share of it plus cash. Okay, still a normal. Okay, but it isn't true for non-normal. Okay. Now, why this is a useful linear transformation we need is because we don't have to worry about the calculation of normal. Why? Because normal, each normal with this small f or big F, right? Because different mu and different thing, right? You have different f, right? Depends on where it is shift around, and depend on sigma, it's more become flatter or thinner, right? Then in that case, we will be using the idea what we call standard normal in the next slide. Okay, you put A1 over sigma, B is mu over sigma, then you can always have a what we call standard normal. No matter what normal, give him any bell, I can reduce my calculation to what we call the normal standard bell. Let me do it graphically. So what I meant is the following. Suppose you have a random variable, mu is here, and sigma is like this. Okay, sigma square. Okay. And if I want to do calculation, say suppose this is A is here, I want to calculate this area. Okay. And then of course, if you how to plot this guy, then you can do the calculation area. That's fine. Okay. But the good thing about this is I can need not to consider this guy, but I consider the Z, okay, which is Z is normal CO1. That is a bell curve located at 0, symmetric about 0, and variance is 1. Okay. And in that particular case, this mu go to 0. Okay. And where's the A? A is A minus mu over sigma. Okay. It's where it locate because you know this two number, right? And the area of the green area, same as the orange area. So as long as I know the green area, I know the orange area. How to find the green area? This is the called Z table, which we give you. Okay. The Z table is the big F. Okay. And big F is the area on the left-hand side, which I will show you in 1 minute, but that is ID. Okay. We'll be doing all this all the time because the bell curve is so common, right? And we can't really show you all the calculation. They always go back to this one. Okay. You ask, okay, since computer so fast, why don't we just compute all the time? And in the even computer, they don't do this calculation. Excel can do it, but they actually go back to the same thing. Okay. No one actually calculate all the time. So even the computer would do the same procedure as we are doing in our head. Is that okay? So let's go to the example. If there's no question, let's go to the example to show you how to work out this. Okay. And the first thing is because the bell curve is symmetric, it doesn't really matter you look at left or right. So if you look at online, they will have the version that the f of z is going to negative or on the positive none. But in the slide, I give you everything. Okay. So you don't have to choose. Okay. Whether you pick the negative one, positive one, bring them all, then your life is easy. Okay. But of course, if you want to save the worth, then probably print one only, but you can bring all of them. Okay. And the reason why it's like this is because of the following. Why you don't have the two? The reason is the following. I have the Z is here, 0 is here, right? And Suppose I only have the negative value, right? I only have negative value. How can I have the positive value, right? Suppose I have 1, right? I want to find this guy. Okay, suppose I want to find this area, right? Right. What's this? This is this area will be f of 1, right? And suppose if I have the table positive number, then I'm done, right? But if I only have negative table, f of negative number, how can we do that? The idea is use the idea of symmetry. Okay. Why? Suppose I have the number -1 here, right? I have negative number table, so it means that I have all the blue number. I can find the blue number. This blue number, what -1? This area is f -1, which is come from your table, right? And this number, because symmetric, same as this number. 1 minus blue, orange. Symmetric. Okay. So this again, which means what? F of 1 is equal to 1 minus f of -1, right? So of course, you don't have to use this trick because you print out the 4 table there. You print out the table, then you don't have to worry about that. Okay. But in case you don't, then this is how you do it. Okay. Because you look at the web, it's always either give you one or the other. Okay. But in my slide, I give you everything. So if you don't know what to choose, be an adult, choose both, right? Only kid would choose, right? You're adult, so you can print everything there. Okay. So why not both, right? So you just know. Now let's give an example of this because this is most important. So we'll spend in this and then we'll call our day. So first is how to do the z less than 1.4. Okay. And this is asking like this question. I have a z. 1.4 is the right hand side. I'm asking ourselves what's probably less than 1.4 over there. Okay. And how do you figure this out? This is coming from table below. Okay. And this is negative. So the first thing I can do is I can do the -1. Okay. And do 1 subtract from it. Right? I can do this guy, 1.4. 1 subtract from that. Why is the case? Remember the question is less than 1.4, right? So let me draw a picture there. Okay. Now the question is 1.4 is here. 0 is here, right? The question is, okay, I want this guy, right? Probability less than or equal to this, right? This is area, right? This is F, right? This is Z here. I want this orange area, okay? Either you just read this from the table, but if your table only given you is this guy, 0, -1.4, right? You only have this table, right? But this is -1.4 is same as this area, symmetry, right? So you just have take the green one and 1 minus green one gives you orange. Okay. Of course, this is one from negative, but of course, as I said, why just use the negative one, right? Just go to the table, look for the negative, just instead of negative, go to positive. Just this one. Then we're done, right? So we don't really need to do it. So as long as you print everything, then you don't have to look, right? So that is what I expect you to do. I mean, you please print that out. I mean, if you go to exam theater, don't forget your Z table. Okay. Now, once to the Z table, the next question is less than -1.6. Okay. The easiest thing, of course, go to negative table, then you're done, right? Go negative table because looking at the area on the left hand side, right? Because what it's asking is look at this left area. This is exactly the F, right? So it's exactly this guy. 1.6 is here. Okay. How you read this table? You read the row first. Okay. And if you want the common places, you read the column. So look for the red table. Look for the row. Okay. The first 2 number, then you look at the column. So if you this is negative 1.61, okay, this number will be negative 1.61, right? Now the next part is what happens if I'm asked negative 1.6 and 0.6, 0.4, right? Okay. And you look at this will be just the blue minus red is purple. Okay, let me show it to you what I'm doing here. Okay, let me draw a picture here again. All right, so we have this 0 and a bell 1.4 negative 1.6. The question asks you how likely that the random variable is between these two numbers. It's the orange area. Okay, the orange in between. But you know our set table is giving me what? Area on the left. The F is area on the left. Okay, so what we're going to do is something you do in the kindergarten. Find the red is what? F of negative 1.6, right? Which we showed how to do it. And we do it again to the blue area from 1.4 left hand side all the way, right? Blue, right, is F 1.4 is the area on the left hand side. Blue minus red is orange. Okay, that is what we do, right? That's how we figure out this probability, right? And that's it. That's all for today. And then after that, we will go into talk about this particular rule, it's called the 2 sigma rule. We'll be saying that why you learn in management, why everything become 2 sigma, everything become 2 SD is because look at the table, 95% of things within 2 SD. Okay, we'll talk about this in the next class. Okay, see you on Friday.